Hi, welcome back. This is session B of part 1 from track C computer science. We are looking at foundations of computer science for AIPMs. In the session A, we looked at why a PM should learn computer science foundations, data structures, and so on. And we looked at approximately 8 to 9, 8 data structures. In this session, which is session B, we are going to look at algorithms, where we are going to look at sorting, searching, breadth first search, depth first search. We are going to look at DP, which is dynamic programming. Then we're going to look at uh, greedy algorithms. Then we are going to talk about complexity, why it is a power tool in PM's hands. Finally, we are going to look at how to negotiate with engineering team, what questions to ask, and finally prepare for interview, and which part of these slides are primarily focused towards interviews. We are going to look at that. Just a reminder, you'll not implement any of these algorithms, but you will have to reason about why you're using a certain things, negotiate with engineering teams, and finally structure the cost or build the systems around those cost structures. So this is very important. As we progress, we are going to dive deep into these. Let's begin with algorithms. We are going to look at 5 families of algorithms today, and each one shows up in our product as a latency line where it delays the deliveries. We're going to look at from the angle of bill and also as a quality ceiling. We're going to look at how we are going to negotiate between these three as well. Let's begin with the algorithms. We are going to deep dive on sorting, searching, breadth first search, depth first search, dynamic programming, and greedy. Sorting. This powers the ranking pipelines and re-rankers. Every search result that we get, every recommendation that happens is typically a sorting algorithm running behind. If you're looking at searching, what began as a uh, lookup for data has evolved into a complex search mechanism now. If you have indexed data into a vector database, now you're trying to search for that required context and content to map or match and then retrieve the results. So here searching is used. You pay once to organize and then query, which is faster. Then we're going to look at breadth first and depth first search against the knowledge graphs, where how does it differ on us going deeper on a particular tree versus us going broader on a particular tree, and then searching for the required data. Dynamic programming, not every time we will have to recalculate or recompute the same sub problem or problem again and again. What we could do is we could cache it and refer to that cache every time so that we have a faster mechanism to solve problems. Then we are going to look at greedy algorithm. In this, we are going to talk about how an LLM picks its next token. Okay, greedy algorithms typically optimize for locally best options, and then they do not focus on the global best. What we are going to look at is alternatives that help us also find the global best options. The common question that will run across all these 5 families is, hey, what does this cost and who decides the bound? Let's start with sorting. Sorting in the simplest sense is arranging a collection of items in a defined order. It's the cheapest way to buy structure, and structure is what makes every operation faster in the future. Okay, I think at this point in time we should make it very clear that there are two things that a PM should hold on to. Hey, sorting also has a provable speed limit. You cannot go beyond a certain limit to engineer the performance. Yeah, sorting is often more work than you actually need. Knowing when to skip it is where the money lies. And there is a bottom ceiling beyond which we cannot reduce the performance, and that ceiling or that floor is O n log n, the order of n log n. And no comparison based sort has beaten this performance beyond this, and that's why it's called the floor, and it's not a guesstimate, it's proven using performance data. Python sorted function uses tim sort, which is of the order of n log n, which is the worst case or the big O notation for sorting algorithm. The recurring shape is always that, hey, you score every candidate and you sort by the score and you take the top k. Yeah, that's how the recurring functionality in AI works. Okay, when you look at the surface versus the sort functionality for search results, yeah, you rank the documents by the relevant score and take the top k. In the recommendation feeds also, if you're looking at Amazon where you get recommendations, the items are ranked by their predicted engagement score in the past. Okay, you are looking at re-rankers where you are trying to reorder a retrieved shortlist. Yeah, even in that we are trying to do sorting using similar mechanisms. Leaderboards or eval scoring, all are dependent on sorting. Yeah. Why do the ranking pipelines and the top k rank is looks like a trap for us? Okay, this is very interesting to understand. Yeah, if you only need the top 10 results, then sorting becomes easier. Imagine if you had to fully sort 1 million candidates to display top 10. You're almost doing 999,990 unnecessary comparisons. Okay, the better option would be to use a minimum heap at O n log k, which considerably reduces the performance time, or you could use np arg partition at the order of n. This also guarantees the k smallest or largest elements are in place, which is unsorted among themselves. But that should be fine because we are looking at the order of n. Yeah. Remember this identification, hey, I need only the top k elements, is a design review level topic, and PMs should discuss this initially. Okay, so imagine if you're trying to sort 1 million candidates, it will cost you approximately 20 million operations. Yeah, but a heap with k is equal to 10 will cost you approximately 3 million arg partitions, or 1 million comparisons. Okay, the gap compounds across millions of daily queries. It's not just in the beginning, but if you had to use multiple users coming in asking multiple sorts, then the right choice of algorithm is very important here, because it will considerably reduce your infrastructure spend. Yeah. it- the only question that you need to keep asking in any ranking system is, hey, do we need a full sorted list or just the top k? Yeah, the answer will change the choice of algorithm, the cost, and the latency involved. Let's look at searching. Searching means finding one item among many, and there are two typical approaches that you can take for this. You can do a linear search, or you can do a binary search. In linear search, when the elements are unsorted or they are not arranged in any specific order, you start from the one, you iterate through the elements, and finally, if you find the element, you return that element. Yeah, in this process, our algorithm, we check every element one by one. We check what works on that data. This works on any data, whether it's sorted or not. Yeah, with 1 million items, you may perform 1 million comparisons. That's why it's of the order of n. So if you had 1000 elements, at max you will be doing, in worst case scenario, which is big O notation, in worst case scenario you will be doing 1000 comparisons. Imagine the element being the last. Yeah, if the number of elements is 1 million, you will be doing 1 million comparisons. If there is a billion elements, you will be doing billion comparisons. So that's why the order of n is applicable for linear search. But in binary search, when the elements are sorted in the sequence, what we do is we split that into precise half, and then we say, hey, is this number too small or too big, and on which side it will live. So every comparison is taken place at half the elements. That's why if it is 1000, for 1024 we just need, which is 2 power 10, we just need 10 comparisons. At 1 million, which is 2 power 20, approximately, you need 20 comparisons. 1 billion, you just need 30 comparisons. Compare this with 1 billion and 30 comparisons. Huge difference. And that's where the time complexity comes from. Okay, every element must be checked until the target is found. That's linear search. You split the data into half, and then you search on the left and right. So half of the elements you are eliminating at any given point in time. That's why binary search is a little faster. The upside of linear search is it works on data, you need not have it sorted. The catch on the this side is it only works on sorted data, so there is an additional compute required to sort the data. Yeah, linear search is the baseline, it always works, but structure buys speed. So every comparison eliminates half the remaining candidates, and that's why we have the order of log n. Okay, the canonical trade would always be that hey, you pay a one-time cost to sort the data and impose structure, so every future query is cheap. Okay, and Python's bisect module is using this binary search, and vector indexes apply this exact bargain at scale. Yeah, they build structure once and search fast forever. Why halving or splitting it into half is really fast. We just looked at these number of comparisons. At a billion items, only 10 more steps are added to the comparison, so this means the cost is barely moving. Yeah, so even if you quadratically increase, or to the power of 10 increase the number of items, the number of comparisons are hardly increasing. And that's why the binary search is so fast. Let's take an example. Okay, you are in a library and you need to search for a particular book. Yeah, imagine there is no organization of the book. The books are scattered on shelves. You have to find one book, then check for the other shelf, then search for the book, and so on. In this manner, you will have a linear search of order of n. But if it is with organization, you know correctly to which section you have to arrive, find the book faster. Yeah, you'll either go to the mid section or split it into half and then go on. Yeah, the library spent time organizing once, and now every visitor benefits it. Yeah, so that's why we keep saying the principle is spend time in organizing data once, so that every future search is fast, because there is a one time cost, and every every search utilizes that marginal improvement that we are making in the beginning itself. Taking this from binary search to vector indexes. In vector indexes, we are indexing the data. For example, in step 1, imagine there is no indexing and you have 100 million embeddings to do. Query will arrive, it will compare with against all 100 million records, O of order of n every time. This will be extremely slow. Okay, but what if we build an index around this? We organize the embeddings, we group by their proximity, pay the cost in the beginning. That is when we are organizing the embeddings. Now the structure is stored and it is ready to serve. What would happen with this is when the query happens with the index, query arrives, it searches on a small subset. It will skip most other vectors. It will The performance will be near to the order of log n. Yeah, the results will be much faster. Why the vector index exists in the first place? Because brute force comparison for at every embedding is pretty bad, and that's why indexes like ANN, which is approximate near neighbor indexes, have come up. Yeah, what they do is they build the index once, which is expensive process in the beginning. It's a marginal cost compared to our compute of doing all the comparisons later. Okay, each query searches only a tiny of the fraction of the content or items, and using ANN, it trades tiny accuracy loss for massive speed gain. Okay, the index acts as the sorted library. So since it is structured, it's easier for us to now do the comparison every time that we need for. Now we are going to look at BFS versus DFS, which is graph traversal. In the session A, we looked at data structures. In the data structures, we looked at how um, tree was one approach, graph was another approach. Okay, tree could be a directed acyclic graph where there are no loops. In a graph, there could be loops that could be formed. Okay, in graph, it's a collection of nodes connected by edges. So for example, A is connected to B is connected to D and E, B could be connected to C as well, E could be connected to C as well, and so on. That looks like a graph. Okay, How is this relevant in agent connections? Like we saw in session A, agent planning. Yeah, breadth first search. Okay, let's look at the strategies one per graph and then come back to this. Okay, in breadth first search, it explores level by level, as in it first finishes A, then it's go to B and C, then it goes to D, E, F. Yeah, like it's listed in the order here. Now if it is a depth first search, it will take one branch and go deeper and deeper, and then come to the other one, and then come to the other ones. So if it starts at A, then it will go to B, then to D, then it will come back to B and go to E, then it will go to the other branch, which is C and F. You see A, B, D, E, and C and F. Yeah, this breadth first search is more like first in first out. That is, you take A, then you B, C, then you go to D, E, F. But this stack depth first search is like a last in first out. You trace one, you find the element or not, you remove that element, come back, put the other element, remove this element, come back to this element, then you add this. So this is more like a stack that you're following with depth first search. Breadth first search is first in first out queue. Okay, this finds the shortest path by hops, whereas this does not guarantee the shortest path, because you're going deep first, coming back and going deep again. Okay, this could take a lot of time. Okay, that's why this uses more memory, because it has to make a note of all the elements in memory. But this uses less memory because it, at any point in time, it has only one path in its memory. This is better for nearby answers, where breadth first says that, hey, if from A, if the answer is either in B or C, breadth first search wins, because it quickly checks A, B, A, sorry, A to B, A to C, A to X, A to Y, and so on. It checks all the nearby elements, and then it works. Whereas a depth first search is good for deep exploration, for reasoning systems, where you have to literally go very deep and then come back. So depth first search excels there. How is this relevant to AI first connections? Imagine the agent is trying to do a plan. Yeah, in breadth first search, it could look at many more plans shallowly, as in it could look at 5 to 10 plans first to begin with, and not go deep on each plan. Whereas depth first search will take one plan, go deep, look at whether that plan will work or not, and then come back. Okay, multi-hop rack systems also work on a similar this tree of thought process also works on this, because in tree of thought, uh, the graph of possible reasoning paths keeps expanding into a very deep network of elements, where each element is like a reasoning step. Yeah, in a tree of thought, it will create a list of steps, thinking, saying that I am thinking this, and if it doesn't, it will have to come back to the top and start again from there. Okay, every traversal step will cost GPU time, latency, money, and safety. Yeah, so the question that you should be asking is, hey, how deep or wide can the agent search before we stop? How deep can the agent go with safe search limits, preventing infinite loops? It's not loops, it's loops, or runaway reasoning. More search can improve answers, but it will incur cost, more and more cost. Okay, so that's what this whole slide is about. What I want to tell you at the end is, BFS is the right choice when the answer is nearby, like we looked at. If the answer is very close to the starting route, use BFS. But the memory cost grows with every level explored, because you have to store all the elements. Whereas with DFS, which is depth first search, it's like stacking plates. The memory is low, but it has to route all, it has to go through all the elements in a particular branch to find the answer, which could be time intensive. So there is always a trade off. The three examples that I want to give on graph traversal are these: agent planning. Imagine you're trying to do a vacation booking using an agent. The agent will try to uh, uh, book a flight A, then hotel ARB, then it will check parallelly flight B with hotel CRD. Breadth first search evaluates as many plans before committing, but depth first search will pick one, go deeper and deeper, and explore it fully before backtracking and coming back and saying that, hey, plan A might not work, let's try plan B. Okay, multi-hop retrieval augmented generation systems, where you're trying to do drug interactions. You're trying to understand how drug will interact with various components. It could be patients, it could be diseases, or any of that sort. Okay, which drugs interact with the medication for the patient's condition. The AL have to walk through like, hey, who is the patient, what's the disease he has, what's the medication given, how will these drugs interact with each other. So three hops across a knowledge graph. That's how rags use the graph traversal system. Tree of thoughts are reasoning paths. The LLMs will explore a particular reasoning path like A, B, and C rather than one path. So they are searching a graph for possible thoughts. More exploration will improve these answers but will also cost more compute. Okay, and this is the trade-off that we are trying to do. At a depth 3, an agent evaluates 20 possibilities. At depth 10, it may evaluate millions of them, making it considerably slower, expensive, and sometimes not providing the right answers, but sometimes potentially best answers. Yeah. The PM question that we just discussed was, how deep or wide can the agent go before we stop? Yeah. Accuracy, latency, cost, and safety are all dependent on that single decision. The running question that we should ask as PMs is always, hey, every traversal step costs me GPU time and money, search limits, and so on, the runaway reasoning, and runaway infrastructure bills. So, what's the optimal path that I should take? We are now going to look at dynamic programming. And dynamic programming is a specific type of algorithm where you break a problem into overlapping subproblems. And if there are subproblems that are repeating, you solve them once, we store them and reuse again and again. Imagine you are repeatedly calculating 28 into 48 or 25 into 48 on your homework every day, every time. What would you do is typically write that answer once, saying that 25 into 48 is equal to so and so, and reuse it again and again. DP or dynamic programming does the same for subproblems. So how does this work? Imagine you have a neighboring tree problem where in tree there are certain calculations to be done. For example, solve tree is used again and again. So ideally what we do is we'll solve this for once and store it in a cache and reuse it wherever or whenever we reach these tree nodes. And how is this used in AI today? We use it for edit distance or Levenstein distance calculations. It stores the intermediate comparison, so no substring pair is ever compared again and again or twice. For spell check we use, for fuzzy matching we use, for sequence alignment we use, fuzzy deduplication of training data. For all this we use this. So how are we trying to connect this? The KV cache that we use in LLMs is actually DP thinking. Yeah. Why recompute attention over all previous tokens when you can cache the keys and values? We will look at this in the next slide. Yeah, this is called memoization. So what we do is we store the results in a KV cache, and that cache is called a memoization table with key value pairs. Imagine the first time you're doing a Sol3 compute and you're storing the answer. The next time you ask for this, it'll look in the cache and reuse that answer. What happens without caching is you compute A, you compute B, you compute A again, you compute B again. But with caching, you're computing A, storing it, and reusing it forever. The same principle applies at all three levels of the stack. For example, in KV cache in LLMs, every time a token is generated, you will need the previous token. So you will have to recompute this token if required. So that means so much token generation. But what VLLMs do is the moment a token is generated, we don't recompute these tokens, we store them in KV cache and reuse them. Yeah, that's how we improve the performance of LLMs. Now, prompt fix prefix caching also is done similarly. Imagine there is a system prompt and a user question that's passed on to the LLM. Yeah, every time system prompt need not be passed to the user question. It can be cached and reused again and again. Tool calls also work in a similar way. Imagine hundreds of users are asking LLMs what's the price of stock price of Apple today. You know, ideally what would do is it will do an API call every time using MCP servers. But what if we can cache that result? If we can cache that result, we can reuse it again and again. You know, with every cache hit that goes, we lower the latency, we have lower GPU cost and the usage and cost. Yeah. So the PM question that we need to be asking is, hey, whenever work repeats, can we compute that and cache it? Yeah. This works for same prompt prefix, same retrieval, same database queries, same API calls, same embeddings, same LLM responses. So whenever there is a certain part of the work being repeated, we can compute it once and cache it. And this brings us to an interesting algorithm called greedy algorithm. Yeah, greedy algorithm is a certain type of algorithm that always chooses the best looking option right now instead of thinking what will happen in the future. It doesn't care about future consequences. So it finds whatever is quick and immediately returns the result to us. Yeah, imagine a person is climbing a mountain. Okay, he always takes the steepest step immediately. Yeah, what this does is he will always go to the local peak immediately, but he might never know what is the global max because he's never looking at, hey, the step that I'm taking towards, is it towards the local peak or is it to a global peak? So he never looks. Whatever is the nearest steepest step, he climbs it. And here image shows the same. So you find the steepest, you find and go here, but you never look at the global max. Imagine agent is given 100 rupees to spend and it is asked to use greedy algorithm. What would typically happen is it will try to maximize the total value immediately. Imagine it has a cost of 100 and there is a value of 100. It will say greedily, hey, I found the best, let's go. It will never go into the other options and say, hey, cost is 60, value is 70, cost is 40, value is 50. You know, if you add B and C, which is 60 plus 40, you get a value of 120, which is the most optimal value. Yeah, just with the same 100 rupees. Yeah, it never looked at the global max. It just looked at what is the local max and it stopped there. Yeah, greedy is fast and simple and sometimes provably optimal. It works in many of the cases, but when choices interact, locking in the best looking option early forecloses combinations that score higher overall. Yeah, it never gives us an option to go to the overall highest score. Recognizing when this is a problem has this structure is a design skill. Okay, we need to identify when are we actually doing this so that we avoid this. Okay, this again talks about the same. For example, in LLMs, when you give the prompt that, hey, the capital of France is, with the highest probability, it will find Paris and it will give you this answer, which is correct. But what if you wanted a little creative answer, like once upon a time, it gives you time. But what if it wanted to say once upon a distant planet, which is a little more creative? It will never go to this because greedy algorithm always finds 70% are the best option locally and delivers it. So what greedy decoding does is it optimizes for maximum speed, zero exploration, one path, always the locally best token. It quickly tries to get us that answer. This is taken care of, or the greedy trap can be escaped using one of these three. One is called sampling. Okay, occasionally we pick a lower probability token and deliver it. That's how we use temperatures for controlling top K and top P values for RAG, for your Gen AI, and so on. You can control these to be a little more creative, less repetitive, and less predictable. Beam search, you can keep K paths alive simultaneously. Hey, though I have found A to be the most optimal or greedy value right now, I'll keep it alive, look for few more. So you're beaming search in multiple directions and betting are getting more. Then you can take a final output saying that which do I want. Yeah, you can only retain the best K at each step. Better final text, more compute, higher latency because you're beaming in multiple directions at the same time. Then there is something called reasoning models. You explore several reasoning paths, compare, and then answer. Okay, greedy search goes in one path, finds or uses particular eval to give a value, then goes in path 2 and 3, so on. Just like beam search, this also has more compute, and this is something called test time compute. Okay, because every time we go in a particular direction, we are doing a testing or evaluation and then returning the result. Okay, and when to use each of these, sampling is best for creative writing because you can control the temperature and so on, and it is good for chat as well. Beam search when you want to do translation or summarization, because we are looking at precision here. Reasoning when you have multi-step tasks which are complex in nature to be solved for. So if you want to go deeper and deeper on particular reasoning paths, reasoning models are the right one. If you're looking for translation and summarization, beam search is the one. If you're looking for creative writing, chat conversations and so on, sampling is the better one. Yeah, each strategy trades speed and cost for quality and diversity, because there is more compute in these two, less compute in this one, and the quality will also be low here, diversity will be high, and so on. So speed and cost are always being traded for quality and diversity. Greedy is fast and cheap. Yeah, sampling adds diversity, beam search improves quality at a cost, reasoning model is giving you test time compute. And this decoding strategy is not something that engineering team has to take care of. I strongly believe it is a product decision, because a PM needs to decide which decoding strategy fits the product, because it talks for experience, user experience, costs involved. Okay, greedy. This is deterministic in answers, evaluations, customer support. That's where it's best for, because it's giving you immediate answers. The temperatures is pretty zero. Yeah, it is far cheap. It is fast, cheap, but can be repetitive in nature or suboptimal. Whereas if you use sampling, we looked at, hey, how this can be good at creative writing, brainstorming, chat, and so on, because it is more diverse but less reproducible. Beam search, multiple directions, it helps you in ideally finding the right translation and summarization. The trade-off is that while we have higher quality, it becomes slower and more expensive. You know, reasoning or test time compute, it's good for or best for complex reasoning tasks, whereas the trade-off is that, hey, while you get the best quality and you get a high latency and cost as well. Okay, the PM conversation that we are going to have is, hey, as a PM, I'm asking always, are we decoding greedily? Are we sampling? Yeah, are we being more creative? Or are we being very deterministic in nature? Yeah, because this will determine the consistency with which we reproduce answers, the creativity. If it is being used for marketing purpose, it is used for sales purpose, we need to be a little creative there. Is it being used for delivering faster responses? Then latency is critical. For cost, how much computation is required here? User experience, does the system deliver reliably or offer more exploration? So that's where the trade-off is always going to be. The most interesting section of session B is complexity as the PM's power tool. Okay, we have two cases that matter most when we are talking about LLMs. One is attention, one is the retrieval. And we are gonna turn all of these into a number that finance can accept when we present them. Hey, why are we introducing RAG? Why are we introducing additional queues? Why are we introducing additional compute power? Yeah, and that's pretty much what finance looks up to. Yeah, they need a reasoning for our investments. So we looked at the big O notations earlier. We said big O is the worst case scenario, big theta, which is the lower match or the upper bound. Yeah, and big omega is the lower bound. Okay, the best option to use is always big O in the room. If somebody is being pedantic, keep the big theta and omega in picture, but we always talk about the big O notation. Yeah, and we always saw this complexity ladder earlier as well. We looked at, hey, if there is a constant, you need to search for that element or find the compute required that grows when the number of elements grow. For constant, it's always one. If it is the number of elements that we have, and we want to do a binary search, etc., it will be in the class of o log n, which is logarithmic in nature. If you had 1,000 elements, you'll do 10 comparisons, but if you have a million, only 20. So the compute barely grows more, or the work barely grows more. Okay, with the number of elements in a array, if you're trying to search or perform an operation like comparison, it's o of n, order of n, which is linear in nature. So if you have 1,000 elements, you'll do 1,000 operations. If it is a million, you'll do a million. This is like 1,000x more, because our number of elements has grown by 1,000x. If it is linear arithmetic in nature, where you're doing to the order of n log n, then this increases the compute considerably. Okay, but if it is quadratic in nature, this blows up, because you're multiplying or looking at comparison between each element in one side of the class with the another element in the same class or a different class. So where each of the classes have n elements. Okay, in that case, it becomes quadratic in nature, which is to the power 2. And if you have 1,000, it becomes almost a million. If it is a billion, it's 1 e to the power 12 in this case. Okay, which is very huge. Now if it is exponential in nature, yeah, I would not even dare to compute it. That's why I put a skull there. And it's dangerous. Okay, it's almost impossible to do that at a scale of million items. Yeah, what I wanted to tell you through this is the gap between on and on square is a million times, is a million fold at this scale, which is at a million items. Okay, a 10 millisecond response versus a 3-hour response on the same hardware. Yeah, so what type of complexity ladder are we climbing is very important, and this big ho hides constants. For small n square loop can beat an o and log n. Yeah, that will be simple. Yeah, but when we go towards the lower end of either quadratic or exponential, it increases time dramatically. Yeah, the exponential wall, if you had to concretely tell, if it is 1,000, which is like 10 to the power of 3, you could go to 30 comparisons. Okay, but if it is like n to the where 20 elements are there, it would take you a million comparisons. N equal to 50, more than 1 quadrillion comparisons need to be done for this exponential sim, with each input doubling the work. Okay, and that's why in attention, o n square is very dangerous. You cannot store every element and or regenerate every other element based on the incoming token. Yeah, that's why this is more work. Imagine if our order of n takes just 10 milliseconds, the order of n square will take hours to do this. Okay, the PM question that we need to resolve for is, hey, what scale are we designing for? Yeah, good engineering is the simplest solution that comfortably handles your expected scale while recognizing when it's time to move away. Okay, and there are two good algorithms to choose. Okay, two truths which both are true. Yeah, one is choosing the good algorithm. At millions of users or billions of vectors, complexity dominates. Okay, o order of n log n versus order of n square turns hours into seconds. We just understood that. Okay, we are not trying to optimize too early as well, because if you're doing, then you're losing on uh, uh, effort. Okay, with 5 documents and 3 searches per second, linear search will answer in milliseconds. But if it is complex and it is growing, then you need to think about choosing the right algorithm. Okay, the art is in balancing these two truths. If algorithmic complexity determines long-term scalability, and we don't have to introduce sophisticated infrastructure before the scale justifies it. So until you're seeing more and more users, more and more queries per second, you don't need to optimize early. And that's why we said attention, o and 2 as the big example we said. Imagine we have a statement, the cat sat on the mat. Yeah, these are the 6 tokens that we are trying to generate. Okay, and these are the 6 tokens. When the processing goes to the sat, the model will ask, hey, should I pay attention to the word the cat on the mat? because if it is here, it'll ask, hey, the cat on the mat. All these words are there, which I should pay attention to. Okay, and each element cannot compare to every other element, because that it becomes the order of n square. Yeah, and if it compares with every token, now that eventually means that every token is looking at every other token, which is the order of n square. Yeah, and why order n square? We just looked at each comparison with every other token, it's n into n comparisons, so n square. Yeah, at 4k to 128k tokens, the jump is 32 times. Okay, the attention work that would be required is 32 square, which is the order of n. Yeah, which is 1000x more time. Yeah, doubling the context is multiplying the cost by 4 times. And this is the reason why the earlier LLMs were small, because the compute power was not enough, and 2K and 4K windows were good enough at that point in time. They were the larger contexts when they were enabled was when uh, the compute power became too cheap. Until then, 2K and 4K windows were the max. Okay, longer contexts need more GPU. They need more memory, and hence they also have a longer response times. You could argue saying that, hey, why not put everything into the prompt also instead of creating a RAG? Yeah, imagine there are 100,000 documents in the prompt, and the quadratic cost explosion will be super high, because we just looked at the number of tokens that the system takes. Yeah. Yeah, how do you avoid or improve what we are doing on the attention of the tokens? Okay, there are three strategies that could be used. One is called flash attention. Yeah, we compute the same attention more efficiently, reducing memory traffic and improving GPU utilization. Okay, this can be done by that sliding window. We only say, hey, each token will only attend to a specific number of tokens, not more than that. Then there are state space models like Mamba, where we are saying, hey, replace the full attention with architectures whose computation grows linearly with the sequence lens. So this could be done as well. These all attack the same problem, that hey, quadratic attention becomes expensive for long sequences of text. You don't need the tricks, you need to know why they are all attacking. Yeah, that's the important part. Sorry for that. Yeah, the total inference time also includes the feed forward layers, the KV cache reads and writes, the memory bandwidth, and the kernel optimizations as well. Yeah, so doubling context does not always make the wall clock exactly 4x larger. It could be much larger because we are including all of these. Yeah, this is in context where we said, hey, doubling the context, where is that here? Yeah, doubling the context will 4x the cost, but ideally it could be more, because we are doing all of these operations as well. Yeah, and as a PM, I will ask these questions. Hey, can RAG retrieve only what's relevant? Does the use case truly require 128k context? How much large latency and GPU cost? Is the long context support worthy the quality gain? Today, many of our tokens being sent to frontier models need not be sent to the frontier models if the use case is pretty small. Imagine if you want to just classify a support ticket uh, into a particular category, you can use an ML model. You don't have to use a frontier LLM model to solve that problem, or you could use a cheaper model like a DeepSeek model or a KLM model to solve that problem. So ideally, you need not send everything to the frontier models, which cost a lot. Then we have brute force vector search, where uh, it doesn't scale as the number of elements in the query grow. Imagine you have a library with 100 million books. Okay, a user asks, hey, find books most similar to this one. So they hand over you a one book, and they say, hey, find books that are similar to this one. There are two ways to do it. One, compare against every book, like we did in the arrays, where you compare or search every element, you try to compare with it. This is brute force. Yeah, you can instead create a smart index that narrows the candidates first, approximate nearest neighbors, is indexing methodology or framework that can be used to index the documents in the right way and fetch the only documents that match the candidate. Okay, so let's take approach one, which is the brute force. Okay, before searching, every document is converted into an embedding. We know this. Okay, if there is a document, we convert it into an embedding of a particular dimension, and this we take and compare it against all the documents in this. Yeah, 100 million documents, they have their own embeddings, and we do a comparison between one document with 100 million documents. This becomes 1.5 into 10 to the power 11 multiplications and additions. So huge per query. Yeah, per query. This is one query, and if there are more, it will grow with those users as well. Okay, imagine if this doesn't grow, at least 1536 dimension doesn't grow, documents will grow, users will grow, both will grow, and still the order of n will still keep increasing. It will keep growing. Yeah, brute force is fine until it isn't. Yeah, that is, on the smaller volumes it works, but when it hits a higher wall and a higher query per second, it becomes very unpredictable. We can never forecast what we will hit. And that's where I said approximate nearest neighbor helps. It helps you build an index so that the number of elements that you hit is small. Okay, how does it do? When you try to index the data or build the embeddings, instead of searching everything, you'll build an index first. uh, let's think of it as an example like Google. When you do a Google search, it doesn't actually go and read every page and provide you the result first. What it does, it creates a super big, super large index, and when you hit the query, it compares against the index and provides you the list of pages on which the data will be. Yeah, this is very similar. Okay, you hit with a query, it looks at ANN index, it finds a small set of candidates and returns those best matches. So instead of doing 100 million vector search, it may check only a few hundred or a few thousand. Okay, and there are few common ANN methods like hierarchical neighbor small world, where a graph connecting nearby vectors is created. The search walks the graph like navigating a city using roads instead of flying over every house. So uh, this is like a graph traversal problem that it solves. Then we have a inverted file index, where groups of vectors are created in clusters. Groups of vectors are it groups the vectors into clusters. A query will actually find the nearest cluster and search only inside it. Yeah, then there is product quantization on its own, where it compresses vectors based on the decimal point. This means it will use less memory, faster comparisons, but there is a loss in precision. Okay, the trade-off is that ANN is fast, but it is because it is approximate. Okay, it might not get you the best results that you are seeking for. We so far looked at how are we solving for a particular angle. We were either solving for cost, we were solving for latency, or we were solving for like recall. And when we implement RAG, we need to look at these three competing goals. Okay, what are those goals? The recall, the latency, and the cost. Okay, recall definitely means that, hey, did we find the actual best documents matching the document that I was looking for? Okay, in latency, we are looking at how quickly can we get an answer, whereas in cost, we are looking at, hey, are the costs of CPU, GPU, or the memory within the constraints that I have set. Yeah, higher recall means that better search quality, lower latency means faster the result and happier the users. The lower cost would typically mean that the infrastructure is cheaper. Yeah, Rema- remember this constraint that you can't maximize for all three. You can only improve one while sacrificing the others. Yeah, this is the entire vector database conversation we will ever have with engineering team. What do you need? Engineering team will keep asking, hey, what do you need? Do you need better recall or latency or cost? Choose the best one and the secondary one, but you can't choose all the three. You can't say that, hey, I want the best recall at the least latency and the least cost. Never gonna happen. Yeah, so imagine there are two products. We looked at this example earlier as well. Yeah, if you are a startup where you have 500,000 documents and you're expecting 5 searches per second, brute force will typically work for us. We need not over engineer the whole solution. But if it is an enterprise where we are saying, hey, there are 100 million documents, 10,000 searches per second, yeah, brute force will be a very costly affair. Okay, whereas your approximate nearest neighbors will become essential. You need to take a trade-off there, because ANN again will not provide the exact results for you. Okay, the scaling wall, this is what we need to notice, that hey, this is the pattern that we'll notice everywhere. Hey, more documents keep coming in, the search becomes slower, and as more users start hitting the search queries, the total work will explode, and the system will become pretty slow. Yeah, so the total work is roughly proportional to, if you can say, hey, total work is equal to the corpus size, which is the number of documents, and into query per second. Yeah, imagine 10 docs and 10 traffic, or 10x the traffic, or 10x the documents increase, 100x more is the search work. You either need to increase your compute power, or need to use better algorithms, yeah, which have a trade-off of their own. Okay, so as a PM, we need to ask, hey, when does our corpus outgrow the brute force? Is it 99% recall acceptable? Or if we need to cut on latency, when does the ANN index turn ROI positive? Yeah, because we have invested money to index the data. When will it turn positive? And that brings us to the most important topic of this whole session. If there was one slide that I want you to always remember forever from this session, is this one. Hey, if we had to talk about complexity, latency, and the cost that we are looking at, this is how I would arrange it. Okay, we need to look at what grows in the system, at what complexity it is growing, what is the per unit cost of that growth, by what volumes it is growing, and finally the latency and the bill that we have to incur. Okay, let's quickly dive into that. Let's take the first step, 1 to 4. Okay, we need to understand what is growing. Every AI system will have something that grows over time. Okay, it can be users, which is daily active users, or documents. If it is a RAG system, it is tokens, because users are giving more and larger queries. Or it could be tool calls, the number of tools are increasing, the number of agents are being put in to the system, or the number of queries per second, because these users are doing more queries now. Okay, you need to ask, hey, what variable will become 10x larger in the next year, or next 6 months, or next 1 month? Okay, and you need to ask, what is its complexity? Hey, at what growth rate is it growing? Okay, for example, reading a cache is the order of 1, but linear search is order of n, sorting is order of n log n, which is like a binary search sorting that we are trying to do here. If it is attention, it is the order of n square, which is quadratic in nature. Exhaustive planning, order of 2 to the power n, which is exponential in nature, and we saw that dead skull on exhaustive planning. So if you were to convert that work into money, how would it look like? Every operation that you're trying to do here will have a cost associated with that, either in milliseconds of CPU or GPU time, your GPU memory, API cost per token, or dollars per GPU hour. Okay, and we need to multiply this into the volume. Hey, are we getting one request or a million requests? Because if it is just 1,000 tokens at $0.01, imagine you getting a million requests per day, which each having 3,500 tokens. You will have the bill of 3.5 billion tokens per day, which is huge. And finally, the last one, hey, will I use a RAG, not use it, or stuff it into the prompt? If you use a RAG, it'll be 3,500 tokens with 20 tokens in the retrieval chunk, and 1,000 in the prompt, and 500 tokens in the response. Yeah. Whereas if you dump all that 2,000 tokens into your prompt, it will give you 50,000 tokens per request, which is huge. And it is 50,000 by this 3,000, which is like 14 times larger. If you don't do a RAG and stuff everything in the prompt, it is 14 times more than the RAG that we have implemented. So if your finance team or CFO is asking, hey, why are we investing in a vector base? You could be the naive PM and say, hey, because everyone is using RAG, it's the trend of the season, it's it's the showstopper this time. But if you are a PM who's strong, you'll say, hey, RAG cuts the average prompt from 50K to 3.5 tokens, which is reducing the cost and latency. At 1 million requests per day, that will be 14 times less token usage. And this is what CFOs want. They want a data backed response to the questions that they are asking. Two forecasts you can make before any benchmark. Okay, attention, we looked at it, it's to the order of n square. um, we looked at how if the context grows from 4k tokens to 128k tokens, the work will approximately grow by 1000x. This means we'll have longer response times and more gpu memory is required. Okay, whereas in a vector search, when you're trying to do queries, you can now use ANN, approximate near neighbors, to combine that power and look at the 1000x cost that you're incurring because your uh, traffic has grown by 10x and your corpus has grown by 100. Okay, now these are the forecasts that we are making, okay, based on the data that it's growing. Okay, as a PM, we need to think, hey, whenever someone proposes a feature, yeah, mentally I want to walk through this chain. Hey, what is growing? How does the computation grow, which is the order of growth? How much compute is that? How much latency will it incur? How much will it cost me? And is there a better infrastructure or architecture that I can use? Okay, always do not ask, hey, can we support 128k context, which is the biggest context that you might want. Okay, rather we should start asking, hey, what's the average prompt length? How much extra tokens will this add? Does this turn an order of n operation into order of n square, which is quadratic equation? What will be the monthly bill at 10x traffic look like? Could retrieval or caching reach the same outcome more efficiently? Instead of me dumping everything into the prompt, can I use RAG? Yeah. And this is a key takeaway from this whole slide, guys. The highest leverage skill isn't memorizing algorithm names, it's translating algorithmic complexity into business consequences. Because ultimately, when you know growth, you understand the complexity, you know what compute power is required, you understand what latency will it now incur, what cost we will incur. Ultimately, you need to take a product decision. Hey, whether we will go with the current architecture, engineering solution, or would we build a new one? And that's the questions that do the work. Okay, we looked at all of this. I'm not going to reread all of this, but there is one question that we did not touch, that we were talking earlier, is on the P95 P99, not just the average. Okay, you need to look at, hey, a great average with an ugly P99 feels broken to the unlucky 1%. And at 1 million requests per day, that's 10,000 angry customers or users on a daily basis. So remember, your SLO, SLA, SLI that we earlier spoke about. SLO is the SLA was the service level agreement. SLO was your service level objective. SLA was your service level indicator. So while SLA is what you sign with the customers, SLO objective is what you set as a target or goal. SLA is the indicator or metric that you keep measuring and start showing the value every time. And that needs to be always good. Do you measure for P95 or P99? That's up to you. But do not make it an average, because average will feel broken. We need to look at P99. Okay. This brings us to the most interesting part of the session, which is the engineering negotiation. While we always why or debate, argue, fight sometimes with the engineering teams, it's always a collaborative effort that we need to look at. And we either underbuilding or overbuilding are both failures, and hence going hand in hand with engineering for the right calibration uh, is really important, and product managers need to do that. Okay, so there are two archetypes that we could look at, two scripts that we could talk about. First archetype is, hey, that's a order of n square problem, it wants scale. So we need not be alarmed in this case. As product managers, we need to ask, hey, does that quantity actually grow? Is n the number of form fields? or n square is nothing. Yeah, if n is documents in the corpus, it's everything. Okay, what if it was n today at launch? What will happen in 12 months? Yeah, where is the first wall that we are going to hit? When is that going to come? And what's the fixed cost? Are we going to do ANN indexing, or what? Are we going to build rags, or what are we going to do? Okay, so the build time, the memory, a new dependency, staleness, is it worth now, or can we do it later? So it's more on the dimension of the time. Okay, and archetype 2 is, hey, we need an index or cache or distributed system. Are we building it prematurely? What does it buy at our current scale? Not measured, but not theoretical. We need to measure how much is the current requirement right now. What will it cost us in the future? Will it be build time, ongoing ops, a new failure mode, cache invalidation, or staleness bugs? So basically, we are asking, hey, what will be the tripwire? When will it break? What breaks if we don't do it? Yeah, for 2 more quarters. So here on the left side in the two archetype 1, what we are talking is, hey, ship the O n square version at 5000 document and revisit at n equal to 500k documents. Yeah, so we are writing the trigger into the document saying that whenever this document size is reached, we will have to relook at this archetype. Whereas on the second archetype, we are saying, hey, protect the team from gold plating as fiercely as from underbuilding. We are saying, hey, don't build the biggest scale right now. Okay, we will build it later. Last but not least, our interview section, we have 6 questions. We have some named examples and numbers. That is what a interviewer will look at. They will not look at vocabulary. Okay, imagine the first question that is asked is, hey, why does an O2 algorithm concern you at scale? Yeah, we know that the cost grows with the square of the input. Yeah, 10x the input is 100x the work, because it is order of n square. Okay, it's great in demo but dead in production, because the self attention is the canonical AI. Okay, its example is something similar that we looked at. 4K increasing to 128K context is 1000x the attention compute. Okay, which is why long context is expensive and slow, and why RAG is often cheaper, because you can't put all the context documents in the prompt and send it. But I would also like to ask, hey, what n is? Is it quadratic in a small bounded quantity? uh, then it's not a issue at all. Imagine they ask you a question like, what's a hash table and why is it everywhere in AI infra? So we know that hash table maps keys to values, and the lookup is almost of the order of O of 1, and it's a straightforward search. Yeah, and we also know that it's the backbone of the KV cache, prompt response coaches, or caches, um, uh, uh, the feature stores, and deduplication logic that we write. Yeah, whenever cost drops because we cached it, a hash table is the reason underneath it. And that's one metric we should always watch, is the cache hit rate. The higher the cache hit rate, the better performance we have. If cache is not being hit, we have optimized for doing nothing. Imagine the third question is, hey, your engineer proposes a brute force vector search for V1. Is it good or bad? This is a typically size problem. Okay, usually good for now, because it is of the order of n into d per query, where n is the number of n is the number of documents, d is the dimension, and at 1 million vectors, which is with a moderate QPS, which is query per second, and it avoids us build cost, memory overhead, and recall loss. So I would ship it with a documented tripwire. We would revisit when the number of documents grow at maybe to 1 million vectors, or when the P95 exceeds the budget. P95 is the response time for from the LLM. It exceeds the budget. We will then move it to HNSW, which is, or IVF, which is the inverted file, uh, documented structures for ANN, which is the approximate nearest neighbors, for indexing the data in the right way so that our search becomes faster. Somebody says, hey, explain caching to a executive. We looked at this, that hey, every time a token is generated, it compares against the existing tokens. Yeah. And if we were to do a generation of tokens every time, it will cost us a lot more, versus if we just cached it and looked at the cache and took those required tokens. So cache helps us avoid regeneration of tokens, which is of the order of n square. Rather, it helps us make it to the order of n. And if 40% of requests are hitting cache, that's 40% fewer expensive model calls. And the cache is freshness. A cache is a copy, so we need an invalidation rule as well the uh, when the uh, when the cache will go stale. So we need to keep a tripwire there. Okay. While this is a stretch question, it could be asked as, hey, walk me through the latency of a single RAG request. We need to look at it from the beginning. That is, we embed the query, we retrieve the top k from the vector index, we optionally re-rank the short list, we assemble it with the prompt, give it to the prompt as an LLM call. We give the prompt to the LLM as a call or a request, which splits into prefill, and then we need to decode it. The output generation and any re-ranker drive the tail. Q8 is the hidden one that only shows under load. That is more number of requests. If it comes, then you have a Q8 time as well. Finally, another stretch question that could be asked is, why are GPUs fast for AI in data structures? This we learned from the first few things, that hey, GPUs work on contiguous arrays of thousands of values, and if they are doing a dot products on top of them, GPUs pair thousands of those cores with memory designed for coalesced access, and hence they are faster. The dot matrix multiplications that they do on this tightly addressed accessible array of data, it's much faster to perform versus the linked list ones. Okay. And this deep learning typically uses these dense tensors rather than the pointer based structures like the linked list that we saw, precisely to keep the GPU fed. And GPUs excel in that particular space. This brings us to the conclusion of session B, part 1 of track C. The only thing that we as PMs need to relentlessly ask every time is, hey, what grows and how does the cost grow with it? Thank you.